And then let's do a share screen. Oh no, this one. So does it work? Yeah, can you see that?
We see you.
Okay, very good. So we're talking about gauge theories, QED and QCD. It's gauge theories. So last time we introduced the Lagrangian. I gave you a short recap about Lagrangians in classical mechanics. Then I introduced the Lagrangian in quantum field theory, which is really the heart of quantum field theory. I mean, that's basically what you learn in the first lectures in quantum field theory. And then we introduced the Lagrangians for the different fields that we discuss here. We have the Lagrangian for the Klein-Gordon field. So for scalar massive particles, we had L scalar was half d mu phi minus half m squared phi squared. Then we had the Lagrangian for the Dirac field. Dirac, so spin half particles, psi bar I gamma mu d mu minus m psi. And then we had the Lagrangians for the relativistic vector field. So massless, this is the photon, LEM was minus 1/4 f mu nu minus j mu a mu. And finally, we had the Lagrangians for the Proca field. So for the massive spin 1 particle, minus 1/4 f mu nu plus 1/2 m squared a mu. And then I stated the most important theorem, which we're going to explore the consequences today, which is Noether's theorem. Which states that every continuous symmetry of the Lagrangian gives rise to a conserved current. Let's write it down. Every continuous like that, yeah. Symmetry of the Lagrangian gives rise to a conserved current. J mu, which is kind of the one of the most beautiful things we have in physics. We're looking for symmetries. Every time we see a symmetry, then we know by Noether's current that there is something which is conserved there. It's a connection between math and physics, right? D mu j mu is equal to 0. Right, and I gave you the example of classical example. Noether's theorem works in every direction, right? Classical as well as quantum. Right, so classically, if we have a particle that is moving in the gravitational potential of another steady massive particle, then the Lagrangian is symmetric with respect to phi. That means that if we have an infinitesimal transformation in the phi direction, right, the Lagrangian looks the same. And that, of course, corresponds to the conserved current, which will be the angular momentum. All right, this is as far as we did last time. Any questions before we proceed? No? Okay. So let's now look at how to apply Noether's theorem to the standard model. So U1 symmetry and conservation. of the electromagnetic charge. So we want to look at a very important example of the use of Nether's theorem in particle physics. And for that, we look at the Dirac-Lagrangian, Ldrock. Remember, this represents spin half fermions, so electrons, for example. Psi bar I gamma mu d mu minus m psi. Now, this Lagrangian is invariant under global phase transformation of the field. Let me write it down. The Lagrangian is invariant under global phase transformation of the field. The key word here, by the way, is global. Right? So what do you mean a global phase transformation of the field? Right? We have a field psi, which is a function of x. Right? Remember, the field gets any value at any point in space-time. And I can transform it to psi prime of x, which is just psi of x multiplied by some phase, I, q, psi. Why I changed the phase, I wrote it not just as high, but as q high, I'll explain to you in a second, times psi of x, which can be written as u of high times psi. So really, I make a division which is not necessary, between, with the phase, I wrote it as a q and a chi. So chi, right, is a real parameter which have some arbitrary value, right? It's of course constant, so it gets the same value at every point in space and time. So chi is a real parameter with arbitrary value. And q is a constant of the model, which is going to be equal to the electromagnetic charge. We'll see in a few seconds why I did that. Or really, this is the coupling constant of the electromagnetic interaction, to be more precise. Right, so this is a real constant, which will be equal to the coupling constant of the electromagnetic charge, electromagnetic interaction. Now I said that the Lagrangian is symmetric under this global transformation, right? So let's show that, right? So Ldrock, symmetry of the Lagrangian. Ldrock is psi bar I gamma mu d mu minus m psi. So when we transform it, right, since u is just constant, right, if psi transforms as u psi, then bar psi will transform as bar psi u star, right? So it's just psi bar u star. I don't even need to put a dagger here. I gamma mu d mu minus m u psi. But since u is constant in every point in space-time, I can simply, the derivative of u is 0, so I can simply take it to the right, and so this is just equal to LB, to the left of the derivative. So that's really just a number, right? So u commutes with anything inside the parentheses. Okay, so I just proved to you that the Lagrangian is symmetric with respect to this transformation. Makes sense, right? A simple transformation. Now I argue that this gives rise to a conserved current. Well, Amy Netter argued that before me, right? This is a continuous symmetry, so there is a conserved current. There is a conserved current, J mu. Right? So conserved current means that such that d mu j mu is equal to 0. So let's find the current. So how can we find the current? In a very similar way as we did when we, in the classical example. Right, so let's look at the change of the Lagrangian. Find the current. Change in the Lagrangian. Delta L. Right, L is a function of psi, d mu psi bar, right? So it's just the L psi, delta psi, plus the L over d mu psi, delta d mu psi, plus delta psi bar, dl over d psi bar, right, plus delta d mu psi bar, dl d mu psi bar, which is 0. Right? Because the Lagrangian is invariant. Of course, I kept the order of the matrices to avoid any, stupid mistakes. Now, changing the Lagrangian when we're making this phase transformation. So at first order, right, the transformation we have is psi goes to e to the I q chi times psi. So we can write down e I q chi, right, is 1 plus I q chi, right? It's an infinitesimal change. Which means, right, that psi, right, just I q chi psi, the first order. Right? And delta of d mu psi, I q chi d mu psi. Similarly, delta psi bar is minus I q psi high, so psi bar, and delta d mu psi bar is minus I q chi d mu psi bar. Right? So take this result, use it in the change in the Lagrangian here. And we have that changing the Lagrangian, Ldrock if you want, we can write as I q I, and then we have L d psi psi, right, that's the first term. And then plus the L d mu psi d mu psi. That's the second term. And then the third and the fourth would be similar, but of course with a minus. Minus I q I psi bar dl d psi bar plus d mu psi bar dl over d mu psi bar. Which, as we state, is 0. So we have the term with the derivative, right? So we had a term here There are two terms. We have this term and this term, which we can write in a simpler form. So we can write dl over d mu psi times d mu psi. That's the full derivative. D mu dl over d mu psi minus d mu dl over d mu psi multiplied by psi. Okay, and of course the same term for the last term, right? So I plug it in, and I find that the change in the Lagrangian is I, Q, I. And then the first term is just the L over the psi. Psi, now I take it outside of the parenthesis. Minus the last term, so minus d mu dl over d mu psi. All that is multiplied by psi. Right, so I took terms number 1 and 2. And now the last term, that is plus d mu dl over d mu psi psi. And of course, similar for the psi bar, minus I Q chi psi bar times dl over d psi bar minus d mu dl over d mu psi bar and plus d mu psi bar dl over d mu psi bar. And all this is equal to 0. Not very complicated math, right? So standard. But of course, why did I do that? What was my motivation? What is this term equal to? Right, guys?
The equation of motion according to Euler-Lagrange.
Right, this is the Euler-Lagrange, which is 0. Right, so this is 0 by the Euler-Lagrange. This is 0 by the Euler-Lagrange. So what we're left with, now I can take the minus I and psi and phi away as well. I don't need them anymore. So what we have is Q times d mu dl over d mu psi minus Q d mu psi bar dl over d mu psi bar. This is equal to 0. Now it's a time to substitute the derivatives, right? We know what is the derivative because we know the Lagrangian. So from the Lagrangian, I actually wrote them down last week. So dl over d mu psi bar is just 0, right? The Lagrangian is, the Dirac Lagrangian is independent on psi bar. And dl over d mu psi is just I psi bar gamma mu. So, and q is a constant, so I can put it in. So this one goes to 0 because the LBD psi bar is equal to 0. And what we are left with, q I can take inside the derivative. So we have d mu q I psi bar gamma mu psi is equal to 0. Does that ring a bell? So if I write down the conserved current as J mu, right, is Q I psi bar gamma mu psi. Then we end up with, as promised, d mu J mu is equal to 0. But what is that? What did we just find out? We've seen this J mu already. Right, you with me? It's not the first time I wrote it. Right? When we discussed the Dirac equation, right, we've seen this current. So in that sense, we did not really discover anything new right here. Right? But the importance is that we saw that we can actually get this same current from the Lagrangian and from Netter's theorem. Right? And the requirement that the Lagrangian be invariant under global phase change of the field. Right? Now you see also why I put down the coupling constant Q in the transformation. Because it explicitly appears in the conserved electromagnetic current. So the technical wording is saying that we transform the spinor under a U1. This is a 1-by-1 unitary matrix, symmetry group. And we say that the conservation of charge follows from the invariance of the Lagrangian under the group U1. This is a technical term of what we just did. Conservation of charge follows from the invariance of the Lagrangian under the group U1. U1 means 1-by-1 unitary matrix. Okay? Isn't this cool, guys? Man, you have to admit this is cool. I don't have to. What we're going to do now is even cooler. Yeah.
One-on-one unitary matrix is just a complicated way to say phase, right?
Yeah. Exactly. But this is a global phase. More? No. Stay. Now I want to do the local gauge, the local gauge invariance. It's much cooler. It requires some explanation because this is kind of the potentially one of the coolest thing you'll see. You know, so far the Lagrangian we have for Dirac, right? This is Lagrangian of a free particle, right? Now, if we want to describe the full dynamics, let's say the full quantum electrodynamics, right? Then we need to address several fundamental questions, right? So that the most important thing is that this Lagrangian does not describe any interaction, right? So the first question we have to address is how can the Lagrangian describe interactions? There is some booster out there. Some of them. Cool. You know, free particle is great, but if you want to have a theory, you know, the theory should not just describe the free particle, but should describe how the particles interact with each other, right? And the related question is, you know, is every interaction allowed, or are there interactions which, you know, not allowed? Is there any certain principle which tell us which interactions this particle can undergo, right? We know that some particles undergo certain interactions and do not go other interactions, right? Some particles interact via the strong force and some others do not. So the question is there any certain principle, or can we think, or does it exist in nature? Is there any principle that states which interactions can be added or are allowed? Remember, in physics, one of the beauties of physics, right? We would like, if we can, to describe the world, right, the universe, in a very simple mathematical terms, right? So, you know, simple principle. So if we can find such a simple principle, you know, it's going to be extremely important. So apparently, in the 1920s, there was a mathematician called Hermann Weyl. Weyl, you've heard the name, right? Sure you have, right? And he worked out the idea that all the known interactions can be derived from symmetries. And around 1929 or so, he suggested the idea of the gauge principle, which means the principle of invariance under gauge transformation. So something like 1929, the idea of gauge principle. Or, you know, principle of invariance under gauge transformation. And this is really a procedure, which I'm going to demonstrate to you right now, of obtaining the interaction from the free Lagrangian, which is symmetric with respect to some continuous symmetry, by taking a global symmetry and localizing it. So we want to have a localized global symmetry. And in order to get that, we must add up some additional field in such a way that the extended Lagrangian is going to be covariant with respect to the extended group of local transformations. I know that sounds a little bit abstract, but let me show you that in a moment. So let's demonstrate that. So maybe I should write it down. So take a free Lagrangian, that is symmetric with respect to a continuous symmetry. And then localize the global symmetric group. Now, in order for that to still be a symmetry, one must include additional field in order to maintain the symmetry. One must add a field. In such a way that the extended Lagrangian is covariant with respect to the new group of local transformations. This is going to be the interaction field. Let me demonstrate that. Example, right? A simple example, classical, of course. Let's say we have a function, f of x is a function, right? Now, we assume that the space is uniform. This is what we normally assume, right? We don't say anything about space. Then the value of the function, let's say we know that the value of the function at some point x, right? The value of the function at some point f of x plus delta x, right? So consider a function f. Then the value of the function of f at x plus, let's say, dx, right, is f of x plus dx f of x times dx. Plus corrections. So in general, it's not going to be the same value, right? Unless, of course, f happens to be constant. Whale idea was to change the space, okay? So he proposed basically to change the scale, the unit of measure. So Whale says, let's change the scale. That's why it's a gauge, that's the name. Change the scale, which is the unit of measure. Of space. Right? So if in addition to the change of f, right, the space, let's say, stretches, right? So if the space stretches, right, from point x to point x plus dx, right, by a factor, right, 1 plus s dx, right, s is the total of this space, between x and x plus dx. It's the gauge, if you're ever wondering where the word gauge came from. Right? Then it means that the value of the function, then the value of f at x plus dx, right, is now f of x plus dx is f of x plus dx f of x times, space now stretches, 1 plus s dx. So this is f of x plus dx f of x. But now we also have f of x times s. Right, all this dx plus corrections, dx squared, which we can ignore if x is dx goes to 0. So the first order, right, the increment of f, delta f, right, is now dx plus s f times dx. Right? See what he did here. Says, okay, I'm changing the function, but now I'm changing the scale in which I'm measuring the space. Basically, I'm changing the coordinates from x to x plus dx. It very much resembles the ideas that Einstein used 10 years before him in general relativity, right? Right. So, the idea is to write down the theory. We want f to be invariant, right? So we want what Weyl did was to modify the differential operator rather than use dx, right? The simple differential. He now use dx plus s as a new differential, and of course we have a new addition here. So this new addition is to be identified, for example, as the 4-vector potential in A mu in electromagnetism, which is identified with this change S mu. So e.g. in electromagnetism, right, S mu is to be identified, or I should say the opposite. A mu is to be identified with space-time dependent generator S mu. So what I was really proposing is to associate the electromagnetism with geometry. Right. That's what we have here, really. So associate EM with geometry. Geometry. Now we try to implement that over the entire physics. Now you understand that this is in the heart of pretty much all modern physics, or not all, right? But big portions of modern physics. When you look for extensions of the standard model, people pretty much follow these same steps. It doesn't work, that I can tell you. But of course, the idea is so beautiful that it works in the heart of many modern theories in particle physics. And it turned out that within the framework of the standard model, it does work. We're actually going to show that right now. So it's such an important principle, this gauge principle, which is with the same stepping, the same footing as the Hamilton's principle in classical physics. Right. Of course, this has a huge influence on the entire modern physics, and the same is that gauge principle. So let's gonna see how it works in the context of the standard model, which we're interested in. Okay, so this is the gauge principle, right? According to Weyl, that's what made Weyl such an important figure in modern physics. Okay, let's see how it works. In fact, I'm going to show you the entire quantum electrodynamics is going to be derived from applying the gauge principle to the Dirac Lagrangian. So let's do it right now.
Seth?
Yeah.
I'm slightly confused with what just happened. So you're stretching space by some scale.
Yeah.
I'm not quite sure how to phrase the question, but I'm not quite sure how to understand the stretching of space and how, like, how do you know to associate this with the electric potential? What is this? Are you just telling this to us, or are we supposed to understand the connection at this point?
I'm gonna just do it right now. I'm gonna do it right now.
Okay, and when you say that we stretch it by S, so S is just some arbitrary number?
Well, it's not arbitrary because I'm going to require the Lagrangian being invariant.
Okay, and so what is the exact transformation? It's not, you're not replacing dx by 1 plus s times dx, right? It's a little more complicated than that.
I'm going to do it.
Excuse me?
I'm going to do it right now.
Okay, so I'll keep my question.
I'm going to do it right now.
Okay.
And the idea, okay, let's go back to the logic. Dirac Lagrangian is great in describing spin half fermions, such as electrons. But the Dirac Lagrangian does not describe any interaction. We don't have interaction, we just have free particles. Dirac tells us how these free particles move. It tells us that we actually have, spin up, spin down, and two antiparticles, one with spin up and spin down. But it doesn't tell us anything about the interactions between these particles and other particles, right? Now we know, right, experimentally we know that some particles interact with other particles, and some other particles, sometimes they do not interact. So we want to know how the particles interact, right? What Weyl said, the idea of gauge symmetry or gauge principle of Weyl says, look, we can get these interactions by requiring that the Lagrangian is invariant, not under global symmetry as we just did, but under local symmetry, right? But of course the Lagrangian, if we just try directly, it's not going to be invariant under local symmetry. And you see right away why from the example we did, 20 minutes ago, right? Because the matrix U, if it's local, I cannot commute it with the d mu, which is inside the parentheses, right? So I have to add up a new field. And this field has to transform in a certain way. And if I add up this field, and this field is, I demand that this field is transformed in a certain way such that the Lagrangian is going to be invariant, right? Then I could retrieve back the, I now have a new Lagrangian to be Dirac Lagrangian plus some extra field, which will be introduced to the Lagrangian. And this is going to be precisely the field that will describe interaction and keep the Lagrangian invariant, but now under local symmetry. That's the beauty of it. So by looking for symmetry of the Lagrangian under local transformation, I can derive the full set of interactions that the Dirac particle can undergo. Just an amazing.
So what you're saying, if I understand correctly, is that interactions change, I don't know, space or the particle's behavior locally, but you kind of want to swallow that change into a gauge field and find conditions on that gauge field. Is that the idea?
Exactly.
Okay, great, thanks.
That's why it's called the gauge field.
Right, because you rescale. Okay, I see. Great, perfect, thanks.
So let's see. So we had the transformation which was global. So now let's look at the local symmetry. So now apply to Dirac Lagrangian. So when we say a local symmetry, right? Local symmetry, or also a gauge symmetry. That's another name, right? Gauge symmetry. Is ones that involve the local transformation. involves local transformation. So that means a transformation that does depend on the space and time, right, as we wish. So we had the global U1 transformation, so now we have a local U1 transformation, so local phase transformation. So a local phase transformation. Or local U1, right? Psi of x, just as we did, goes to psi prime of x, which is EIQ chi, but now chi is a function of x. Psi of x. Right, so now chi is not just a number, but is a function. It's a well-behaved function, right? It's continuous. I don't need to worry about it too much, but it's it's still a function of space and time. Right. So what happens when we apply this transformation to the Dirac Lagrangian? So Ldrock, right? Is psi bar I gamma mu d mu minus m psi. Now we have a local nature of the Gauss transformation. So I cannot just take the u and commute it with the parenthesis, because I have the derivative, right? D mu inside the parenthesis. So the u is not going to commute, because I have the d mu here. So with the transformation, apply the transformation, LD or L will go to L prime, which is I. Now psi bar is E minus I U chi psi bar, gamma mu. Now I have the d mu psi, but now psi goes to EIQ chi psi. So I have two terms. The one would be EIQ chi d mu psi, and the second one would be the plus IQ d mu chi EIQ chi psi. Then the second term, right, that's the easy term, minus m E minus IQ chi psi bar EIQ chi psi. So I have the original Lagrangian, but now I have this extra term, right, which originates from this derivative of the chi. So this would be minus, because I and I get a minus, so it's a minus q psi bar gamma mu d mu chi psi. So what we just show is that we take the free particle Dirac Lagrangian, or free particle Lagrangian for the Dirac field, and it is not invariant under U1 local phase transformation. Right? So the Dirac Lagrangian is not invariant under U1 local phase transformation. Okay, nothing surprising, right? I would be very surprised if the Lagrangian would be invariant, right? Nothing special, right? Now, we said we're going to follow the gauge principle. So we want to make the Lagrangian invariant. So in order to make the Lagrangian invariant, right? So we have to add a new term to the original Lagrangian. And we have to determine the transformation law of this term such that the Dirac Lagrangian stays invariant, right? So determine the transformation law of this term such that the Lagrangian stays invariant. But this is pretty much what we did when we derived the Dirac equation in the first place, right? We chose some transformation law of the spin or psi such that the Dirac equation is invariant under a Lorentz transformation. So the required gauge invariance can be restored by if we replace the derivative d mu of a free particle with a covariant derivative. So in order to do that, to achieve that, right, we replace d mu with what is known as the covariant derivative and the symbol is capital D, d mu. So d mu goes to d mu, which is equal to d mu plus an extra term, which I'm going to write as IQ A mu. And A mu here is a new field. A mu is a new field. At the moment, I'm not going to say anything about this field. Although I guess that some of you can guess what field is going to be. Right. Remember, we had this unwanted term in the Lagrangian. Right? This was the term we don't like. And we want to cancel it. Right? So in order to cancel this term, right, we can do that provided that the field has its own transformation law. So cancellation of the extra term in the Lagrangian is achieved provided the new field transforms as a mu of x transformed to a mu prime of x is a mu of x minus b mu pi. Now we can see that immediately by simple substitution. Right, so if we substitute, right, I psi bar gamma mu d mu, right? We change d mu with the capital mu, so now it's going to be d mu plus IQ A mu psi. How does that transforms? So that transforms into I psi bar E minus IQ chi gamma mu V mu plus IQ. Now A mu is going to be A mu minus B mu chi. E I Q chi psi. They switch the order, but it doesn't matter. Psi and E minus I Q chi would commute. So this is going to be I psi bar E minus I Q chi gamma mu. And then we had, again, we had these two terms, right? So we had E I Q chi. And we had two derivatives, one of psi and one of the exponent. So I Q d mu chi psi plus d mu psi plus IQ A mu minus d mu chi psi. But d mu chi, what did I wrote psi? Right, but of course, this extra term, which bothered us, was canceling this last term. So this is just I psi bar gamma mu d mu plus IQ A mu psi. Voila. Again, I did two things. I changed the derivative with a covariant derivative, right? D mu will change to include now an extra field. And this extra field, I required that it transforms under this local gauge, will transform in a certain way. A mu would go as A mu prime, which is A mu minus D mu chi. And when these two conditions are met, then the modified Lagrangian is now invariant under local gauge transformation. So we just proved that the Lagrangian, that the modified Lagrangian, L, which is psi bar I gamma mu d mu minus m psi, that's right, which is, we can write it down in length, right? Psi bar I gamma mu d mu minus m psi minus q psi bar gamma mu a mu psi is a gauge invariant Lagrangian. Four spin half Fermions, of course. Right? Under local U1 gauge transformation. So what do we have here? Well, now we look at the Lagrangian. So we have two terms. What is this term? The first term.
The regular Lagrangian, the global variant.
What does it represent? This is the
particle.
It is a free particle, right? This is a free particle. Exactly. Very good. This is a free particle. This is the Lagrangian that represents a free particle. Very good. And what is this term? The second term?
the interaction?
This is an interaction term. Exactly. Right. So this term, right, Q psi bar gamma mu, I can change the order, psi a mu. I can write it down as j mu, a mu. Right. So we have an interaction term, right, between what? We have, what is j mu?
The current?
This is the current, right? This is the current associated with the fermion, right? And what is a mu? What is a mu? I mean, here I just introduced it as a field. But which field?
EM?
It's a photon. Right? But I haven't proven to you it's a photon. I'm going to show you right away. I mean, it has everything you ask for a photon. Right? So again, what did we do? We just found, right, that the requirement that the physics is invariant under local U1 phase transformation implies the existence of a gauge field which couples to the Dirac particle in exactly the same way as the photon couples to them, as we saw previously. Right? So all QED can be derived by the requiring that the invariance of the physics under a U1 local phase transformation. Let's write it down again. That's not beautiful. I don't know what is beautiful in science. Right? We found that the requirement that physics, the Lagrangian, right, is invariant under local U1 phase transformation implies the existence of a gauge field. Which couples to Dirac particles in exactly the same way as the photon. Right. All QED can be derived by this requirement, invariance of the physics on the local U1 transformation. Now, physically, now I'm telling you, right? I'm arguing. A mu term is appropriate to describe a photon. Right? Why do I say that? So, as you know from electromagnetism, right, electromagnetic interactions are described by replacing the form momentum of the charged particle with P mu minus Q A mu. Right, so from EM, right, electromagnetic interaction, interactions are described by replacing E mu to P mu minus Q A mu. Did you see that, by the way? I think we did discuss that here, no? I think we did. Did you see that in EM? Or never? It's a question. It's a yes or no question. Do you follow that in E&M or not? Or you don't remember? Anyone? Very quiet.
I did, but it was a long time ago. Eyal T8 for it last year, so he might know.
You might know. Okay. Of course, A mu is the 4 potential, right? A mu is the 4 potential. Now, of course, when we do quantum operators, using quantum operators, right? I d mu goes to I d mu minus Q A mu. Now A mu is an operator. And I just multiply it by minus I, we get d mu goes to d mu plus I Q A mu. Eh? What is that?
The gauge transformation.
This is a covariant derivative. Right? I just wrote it down. Ta-da. And the gauge transformation A mu goes to A mu minus d mu chi. Which you required from the field A mu. Where else did we see that? I'm pretty sure we saw that in this course. Where else did we see that? Huh? Oh, come on, it wasn't that long ago. Where did we see that? We had several lectures about that. Come on, guys. Huh? No clue? Oh, come on. That is a transformation of Maxwell's equations, which are invariant under, right? When we make this transformation from A mu, when A mu is to be considered as the 4 potential of the electromagnetic field, and we make this transformation, then the Maxwell's equation remains the same. This is the same gauge that you learn in electromagnetism, right? The gauge transformation is exactly same transformation. That leaves Maxwell's equations invariant when A mu is the full potential of the electromagnetic field. And finally, as we just saw, right, the second term in the Lagrangian right? What is that? It's just the J mu A mu, which represents what? Right? Interaction between the photon and the conserved current of a fermion. Right? Exactly what we have here. We did that. Come on, guys. Isn't that beautiful? So yeah, so A mu is a photon, and we just showed that the gauge principle, when applied to the Dirac particles, leave us with an interaction between electromagnetic interaction, essentially, between a photon and a fermion. So we're nearly there. We did most of the work in writing down the Lagrangian of quantum electrodynamics. So let's complete the task. Questions? Any questions? Half of you are with cameras off, so I can't really see you. The other half are just not saying anything. Taking time to digest.
So to recap, you introduce some arbitrary field which you have no idea what it is, in order for the Lagrangian to be invariant under local U1 transformations. And then you realize that the mathematical properties of this arbitrary field are, by coincidence, precisely the same as of the vector potential from En.
Exactly.
This is kind of a happy coincidence.
Yeah, exactly. Exactly.
Okay. I'm not very satisfied by coincidences, but
Well, that's a real coincidence. The point here is to show you that we can in fact derive the entire QED. Remember, what do we really want? What did Whale do, right? We wanted to find a mathematical way of describing all the interactions. So knowing what interactions are allowed and what are not allowed, right? And what Whale found was this idea of gauge principle, which states that it's enough to determine that if we know of a global gauge, if we demand that the Lagrangian is invariant under a local gauge, we give rise to new fields, and these fields these fields really represent interaction. Now I think they knew about electromagnetic interactions by the time Whale did that, but of course there were other interactions which he didn't know about. I hope we'll have time to, at least we'll start to discuss them today, about the strong interactions. And the beauty of the standard model is that the mathematical treatment of the strong interaction is going to be exactly the same as that of the electromagnetic interaction. For the weak field, it's a little bit, for the weak interaction, it's a little bit more complicated because there is the masses, W and Z bosons, so that's why we'll treat them next week. But we saw a little bit of the complexity about the CKA matrix there. But yeah, the mathematical treatment is the same. So yeah, happy coincidence. But you know, there is something very deep happening here. Okay, let's proceed. So the way now I want to do is to write down the QED Lagrangian. Remember, I told you that the standard model Lagrangian is quite big and nasty, but we just take parts of it. We were interested in one part at a time. So we're quite, you know, we're 2/3 of the way, right? Because we have the kinetic term, right, and the mass term for the electron, and we have an interaction term between the electron and the photon. So we still have to have a kinetic term for the photon, but we know what is going to be the kinetic term for the photon because we wrote down the Lagrangian for the electromagnetic field last lecture. So we simply copy that, and what we end up with is that the L QED, right? So we have psi bar I gamma mu d mu minus m psi. This is the kinetic term and the mass term for the electron. Then we have the interaction term between the electron and the photon. And then we have the kinetic term for the photon. And that's it, basically. So this is first term, right? Psi bar I gamma mu d mu minus m psi is the kinetic term. Right, this is propagation of the free Fermi. And then again, that remember how we got that, right? This was the requirement of conservation of the form momentum and the angular momentum. Second kinetic term, you know, minus 1/4 f mu nu f mu nu. This is the kinetic term of the free photon. And then the interaction term. This is the interaction term. Between the photon and the fermion of chart Q. Can you see why I got this Q? Between photon and the fermion of charge Q, right? This is the vertex in Feynman diagram, right? The vertex can connect the photon and the electron. Now, again, notation, right? I mean, we got this photon, right, by the requirement of gauge symmetry of the Lagrangian. So every term that we get by the requirement of the gauge symmetry, or every boson that we get by the requirement of a gauge symmetry of the Lagrangian, how do we call it?
Say again?
How?
Gauge boson.
Gauge boson, exactly. Right. The photon was obtained by gauge symmetry. Of the Lagrangian. Every boson that is obtained this way is called gauge volumes. Okay, and just a few more comments. So more comments on that before we go on. Right, we said that we wanted the Lagrangian to be gauge invariant, right? We added up an extra term, right? This minus the kinetic term for the photon, minus quarter f mu nu, right? This doesn't, this fulfills this condition, right? We had this already when we discussed the photon. So the addition of this kinetic term for the photon here, right? This does not change the fact that the Lagrangian is gauge invariant. LQED is gauge invariant. Right? But we could have done something else, right? We could have done a mass term for the photon, right? But if the photon was massive, right, then we had a mass term for the photon. One half m gamma squared a mu, right? That would transform to 1/2 m gamma squared a mu minus d mu chi, a mu minus d mu chi. And that, of course, is not the same as 1/2 m gamma squared a mu. So this would break the symmetry. And would make the Lagrangian not gauge invariant. So that means, again, there's something very deep here, that if you believe that the gauge principle is the guiding principle that determines the interaction properties, which again, QED is very successful. So, it fully follows for QED. That means that the resulting gauge boson has to be massless. So from a theoretical perspective, again, if you trust the gauge principle, the photon has to be massless. So if you trust the gauge principle, then the resulting photon must be massless. Well, that gauge boson. The theory predicts massless photon. And experimentally, we know it is with the best accuracy we can have. Now, again, this is not true for the weak interactions, right? For the weak interactions, we know experimentally that the W and the Z bosons have masses. They're actually quite heavy, right? We will discuss, I'll make sure that we have time before the end of the semester to discuss the Higgs mechanism, which is the mechanism that gives rise to the masses. So the Higgs mechanism has a solution to how to solve that. Now this is true for the electron. So the QED can work out for any charge, electromagnetically charged particles, or any charged fermions. But if we want to put the QED to all charged fermions, then it's pretty simple. We simply have to sum up over all the fermions. So if we are Lagrangian for all charged fermions. That's quite straightforward. Simply add all the terms. L QED is sum of all fermion sidebar phi, sidebar F, right? I gamma mu d mu minus M psi, well, MF is fermions. MF psi F minus 1/4 F mu nu. That should be enough to describe all fermions, right? And you know, d mu, the capital D, right, the covariant derivative, we have the q that enters there, right, in the second term, the coupling constant, but that has to, we have to be careful because we have to multiply it by the charge of the relevant fermion, right? So for q is minus e for electron. This is inside e mu. This q is 2/3 e for up quark. Minus 1/3 for down quark, etc. Just have to be careful in what you put in. Questions?
I have a general question. You talk about the U1 local U1 symmetry.
Oh.
Actually, you don't add the same phase to all the particles.
You mean for the different particles?
Yes.
Yeah.
Because an electron will get a phase corresponding to minus e and an up quark corresponding to other q.
Well, chi is a general. Yeah, you can have it for any particle.
No, but chi is general. But if you talk about the total QED Lagrangian that you wrote right now,
yeah,
it has only one symmetry, right? It's not a symmetry for electrons, a symmetry for up quarks. It's one symmetry. This symmetry includes different phases for electrons, up quarks, and down quarks.
Yeah, I do want the Lagrangian to be invariant under. So it actually it is actually end up as being the same phase, because I want the Lagrangian to be invariant.
No, it's the same phase up to a constant. You add yes up to multiplicative constant.
Yeah.
That means your theory has the charges as parameters that can be determined however you want. The different charges cannot be determined by QED, right?
You mean if there is something in QED that tells you what is the value of Q?
Or not the value of Q, that's clearly not, but for example, is there anything that tells you up quark must have twice the charge of down quark with opposite sign?
Not within this framework, no. This is a free parameter of the model.
So each charge is a free parameter of the model.
Yeah.
Okay.
You don't get it right away from here.
Okay. And that also means that conceptually, you might have had dozen forces, each with the same photon-like behavior with different charges. There might have been a fifth force, like the electromagnetic force, just with different charges.
Yes, in principle, yes. There might be some, you can think of other terms in the Lagrangians. That's why, you know, this goes to beyond the standard model theories.
Remember? No, what I'm saying is that I'm trying to understand exactly what part of what we're saying is fully theoretical and what needs the experiments to determine.
The coupling constants. The coupling constants, the standard model does not tell you what are the coupling constants. So it doesn't tell you what are the masses, and it doesn't tell you what are the charges. This is something which you measure experimentally.
This explanation does not forbid a fifth force.
No, you can always add terms to the Lagrangian. That's, this is going under the general title of beyond the standard model. Remember, the standard model is there to describe what we know, right? At the end of the day, theory, as beautiful as it may be, is meaningless unless it can provide explanations to the experimental results. And this whole theory was constructed to give some general framework which would be able to explain the plethora of particles that we're seeing and the plethora of interactions, and why some interactions we do see and some other we don't see.
Okay.
So if tomorrow you find out experimentally new particle, new interactions that is not part of the standard model of Lagrangian, then there is meaning that there is something which we're missing in this Lagrangian. As we discussed that in one of the first lectures in the course, right? In particle detectors, there is none, right? All the particles that we've seen has been predicted by this part of the standard model Lagrangian, right? And others. But we know globally that there are things which cannot be explained. I pointed out to you dark matter, some other issues. So yeah, in that sense, we know that this Lagrangian is not complete. But we know that this Lagrangian, as I just wrote down, is an excellent in describing all QED phenomena that we're seeing.
And another question, say we do agree that the U1 symmetry is exact.
Yeah.
Can you add more terms to the QED Lagrangian that don't break the U1 symmetry?
This one does not break in the U1 symmetry. This one is invariant under U1 symmetry. Right?
Yes, I'm asking, is this the most general Lagrangian? No, so for one fermion and one photon.
Is this the most general one?
Yes.
Yeah, I think so. I think we derived this.
Thanks.
Okay, we run out of time. The next thing I'm going to do is to write down the QCD Lagrangian, quantum chromodynamics. It's very nice because the math is going to be exactly as what we did. It's just that the symmetry group is different. It's going to be a more complicated symmetry group. So rather than the U1, it's called the SU3. So this is 3x3 unitary matrices that have a determinant of 1. This is the symmetry group. The main difference is that this symmetry is non-abelian, meaning for the U1, we only had one phase. So there's no problem. But with the symmetry group, with the SU3, we have several generators. So we can think of it as several group members. And the group is non-abelian, which means that the group members do not commute with each other. So this is going to give rise to new terms. As I'm going to show you, it's not very difficult to show. You're going to have 8 such new terms, which are going to be identified with the gluons. And the non-abelian, meaning this extra terms that come because of the matrix not commute, in fact will tell us that these gluons have to interact with each other. So they will give rise to new terms, which will be interpreted as interaction terms of the gluons with themselves, right? We don't have this with photons. Photons, there's a superposition principle that just goes through each other, and they don't know of the existence of each other. But with the gluons, this is not the same. So the beauty, to my opinion, is that it's going to be the same math, but applied to a different symmetry group. And we're going to get up with a Lagrangian that properly describes the strong force. Right? Quantum chromodynamics describes the strong force. It's the same math, just a different symmetry group. And it perfectly describes all the known phenomena of the of the strong force as well, but not just the quantum theory. For the weak force, we had to do a little bit of tweaking. So this is on the upside. On the downside, I was hoping to do more today. Somehow I'm going slower than I'm hoping, which means that there are really parts that I was hoping to cover in this course that I will not have time to cover. And I don't want to rush because, you know, I think I don't mind if you learn some less things, but the things that we do cover them properly. I asked you several times if you feel that I'm going too slow or too fast. Nobody complained. But that's it. I pretty much know what we will have time to cover. So just the QCD, the weak, and then the Higgs, which is kind of crucial. And as I promised, I'm going to give you homework from here every week until the end of the semester. There are not too many weeks left, so there'll be total like 10 problem sets. So on Thursday, we're going to have a tutorial, and then continuing with the strong force. Hopefully, we'll finish it by Thursday. If not, then we'll finish that next week. All right, guys.
All right, thank you.
Questions, comments?
Okay, thank you.
If not, then we can do the stop sharing and stop recording.